Hi, I'm Scott Vaughn, and this video is about the Prague Astronomical Clock. I was so blessed this summer, 2021, to have the opportunity to visit my sister and her family in Prague in the Czech Republic. In fact, my daughter had the opportunity to travel there first, traveling with my sister there before me, and then I followed along later to meet up with them. So my reason for going to Prague wasn't to see the astronomical clock. In fact, when I arrived, I was only just beginning to understand how to read it. But now that I'm back home and have had some time to study it more closely, for example, watching other videos here on YouTube and studying several websites devoted to explaining the clock, I'm now beginning to fully appreciate this beautiful and brilliant achievement of mathematics and engineering and the fascinating history behind it. A big thank you to all those who have already posted videos on YouTube explaining the clock and its history. And thank you to all those that have written about it and posted articles online. And to those that have built animated simulations of the clock so we can all appreciate this wonderful intellectual and engineering marvel that's now over 600 years old. I'll put links in the description to some videos and websites that I've found helpful in learning about the clock and that I'm using here in this video. The Prague Astronomical Clock dates back to around the year 1410. That's over 600 years ago, and thus has a long and complex history that is far beyond what I will try to describe here. And of course, it's undergone renovations and modifications all along the way. I'll leave most of the history for you to discover through other videos and websites, and I'll focus mostly on just reading the clock with this video. Just reading the clock is a challenge, though. The experience of reading time on this clock is really about looking back in time, as it reveals a medieval perspective, an understanding of the world. In other words, there is still a history lesson in just learning how to read this clock. And while we focus on reading the clock, I can't help also think about how much greater still would be an understanding of how it actually works and the design and interaction of all the gears behind the clock's face. The Prague Astronomical Clock is really a mechanical computer built during the Middle Ages. Its design and creation date to a time before the advent of modern science. In fact, it dates back to even before Copernicus created a model of the solar system with the Earth orbiting around the sun. Instead, the astronomical clock very accurately models the apparent motion of the sun and moon and stars, just as they appear to us here on the ground as we look up into the sky from an Earth-centered perspective, just as people did in the Middle Ages. And what a time we live in now. Here we are looking at a modern digital computer simulation available online to almost anyone anywhere in the world of a medieval mechanical computer that was originally built to model, understand, describe, and predict the motions of the sun and the moon and the stars and the changing of the seasons. That's why this is a math video. Math is the tool we use to model, describe, understand, and predict the entirety of the universe. And the Prague Astronomical Clock is a beautiful working artifact of early medieval mathematics and a medieval understanding of the universe. And that's why you clicked on this video. It's the value and reward of the effort and the achievements made toward understanding and describing the patterns of the universe. That reward takes some effort, because this is about much more than just the practical needs of telling time. It's about understanding the universe and our place within it. And with the Prague Astronomical Clock, specifically, this is about an over 600-year enduring effort toward that understanding. So imagine yourself in the Middle Ages looking up at this clock. What would it tell you? I should say there are obviously two huge dials here on the front of the clock tower, an upper dial and a lower dial. And it's the lower dial that's a calendar and tells the month and day and indicates a saint associated with each day of the year. The lower calendar dial was added to the clock in 1490, which, by the way, was even before our modern Gregorian calendar was created. And This would make a great topic to explore further in another video another time, but to account for leap days, every 4 years the calendar mechanism is set back one notch. But in this video, I want to focus on the upper clock dial, the oldest part of the clock, the part that dates back to 1410. So on the clock dial, the outermost band is numbered 1 through 24 in old Gothic style numbers, which are hard to read at first, but as you look closely, you can begin to read them as you will recognize most of the digits. Here's 1, 2, that's 3, 4, 5, 6. This is a 7, 8, 9, 10, 11, 12, and we move around. This is 23, back to 24 again. This outer dial tells what is referred to as Old Italian time or Old Czech time and counts the hours since sunset. And because it's a 24-hour dial, can also be used to determine the number of hours remaining until the next sunset. For example, with the image that we see here, we have 1 hour to go until sunset. In the Middle Ages, it was customary to mark the end of the day at sunset. Marking the end of the 24-hour day at sunset meant this also marked the start of the next day. And it's a very different way to tell time than what we're used to today. And it's interesting to think about this ancient way of looking at the day and to imagine what it would be like if we continued to use that system today. This outer dial moves back and forth independently of the motion of the rest of the clock's face throughout the year to adjust for the changing length of the day, as you can see here in this animation. And as a result, the pointer hand will always point to the number 24 at sunset on each and every day all year long. Now, going back to this image for September 19th, about 6 minutes after 5 o'clock, we see that there's about an hour to go until sunset. So sunset would be about 6 minutes after 6 o'clock at 18:06, and you can see that this app is indicating that up here. Now, if you look up September 19, 2021, sunset was actually at 7:06. So to explain that apparent discrepancy, the astronomical clock is set to Central European time all year long. However, Prague and the Czech Republic set clocks 1 hour ahead to Central European summertime from March to October. So I suppose it's kind of unfortunate and certainly adds to the confusion when trying to read the clock, because as most tourists would be most likely visiting the clock between March and October each year, and so as they try to make sense of the clock, they discover it's 1 hour behind the local official time. But I mean, come on, a 600-year-old clock isn't going to bother with silly ideas like setting the time forward, ahead, and then back each year. I mean, really, honestly, who wants to bother with that anyway? Next, just within this outer ring, you can see Roman numerals here. These count time in the way that we think of it today, but it only tells the hour and not the minute. The pointer hand here is pointing just past 5. Right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So it's counting off 12 hours to midnight here and 12 hours back to noon, and this is just past 5. There is no minute hand on the clock. From the perspective of the clock designers, there just was no need to be so precise as to include minutes. So still, we can estimate half-hour and quarter-hour points between each of these Roman numerals. So maybe half an hour would be when it's right between the 5 and the 6. And we might be able to estimate a quarter past the hour if we look very closely. And of course, in this image, it's just a few minutes past 5 o'clock in the evening. Next, moving further in on the clock face, we see the familiar Hindu-Arabic numbers counting from 1 through 12. Here's 1, 2, 3, 4, all the way to around 12 here. This is dividing up the day into 12 equal periods. Perhaps I should say that the blue region represents day, this red region represents dusk and dawn, and the black region will represent night. And I'll get to that further later, but we see the day divided up into 12 intervals, equal intervals. I mean, these may not necessarily look like equal amounts of area, but the sun will spend equal amounts of time in each of these intervals as it moves across the clock's face. So this is dividing the day into these 12 equal periods, as the ancient Greeks and Babylonians did thousands of years before this clock was even built. In the summer, those 12 equal periods are longer because the days are longer, and those periods would be shorter in the winter when the days are shorter. And each of these equal periods during the day was thought to be dominated by different planets in the sky or by the sun or the moon, just as the ancient astrologers believed that the stars of the Zodiac dominated and influenced life on Earth during different times of the year. So that's why these 12 divisions are called the planetary hours. They're not hours in the same way that we think of them today, as they could be as short as 40 minutes in the winter, and they could be as long as 80 minutes in the summer, and they're about 60 minutes long around the spring and autumnal equinox. Now, there are 12 intervals or divisions for these planetary hours through the day, and of course that's more than the total number of planets, even counting the moon and the sun. So some of the planets, or the moon or sun, had double duty during the day to rule over that hour. On the face of the dial, we can see a region that represents day in blue and regions for dawn. Aurora is the Latin word for dawn. And a region for twilight or dusk in orange or red. That's crepusculum in Latin. The clock face was repainted in 2018 so that the regions that were orange before are now red, and this is a picture during the renovation when the clock face was repainted. Notice also how the letter V was used where we now use the letter U. And of course there is a dark region here representing night. We can see these words, these Latin words, ortis, meaning east, and ocasis, meaning west. So this represents the direction where the sun will rise, and here's where the sun sets in the west. In fact, the areas of these regions for dawn, day, and twilight, or dusk, and for night are designed very precisely. The sun will set in Prague just as the sun on the dial fully enters the region of twilight. And the dark region represents the period known as astronomical night, the period after the sun has moved 18 degrees below the horizon and the sky is at its most dark. This is still the modern definition of astronomical night. And then the sun rises in Prague just as the sun on the dial moves out of the region representing dawn and into the region representing day. There is some fascinating geometry involving the intersection of circles on the celestial sphere and how these relate to the design of the clock. Prague is at a latitude of 50 degrees north, and it's this latitude that determines the circle of the horizon along the celestial sphere. Also important to the clock's design are the projections onto the celestial sphere of Earth's Tropic of Cancer, the summer solstice path, the Earth's equator and the Tropic of Capricorn, the winter solstice path. In summer, as Earth rotates, the sun follows the summer solstice path. In fall and spring, follows the path of the celestial equator. And in the winter, as Earth rotates, the sun appears in the projection of the Tropic of Capricorn in the celestial sphere. The face of the clock represents a mathematical projection of the portion of the celestial sphere visible at Prague onto the 2D plane of the clock face. This projection is called a stereographic projection and maps points onto the 2D clock face from the celestial sphere corresponding to the north-south axis of the Earth's equator, and the Tropic of Cancer and Tropic of Capricorn. I'll talk more about that in a moment. Now, moving further into the interior of the clock face, we see the symbols of the zodiac prominently displayed and the position of the sun within the zodiac marking out different times during the year. The last column in the table indicates the sign on the first day of each month. Notice that the signs of the zodiac advance around the 20th of each month. So each sign here represents about the last week of the previous month and 3 weeks into the following month. The position of the sun on this dial indicates the constellation in which the sun will rise each morning, according to the traditional dates of the zodiac in astrology, as shown here. These are the dates in which the sun rose in each of the constellations of the zodiac in the time of the ancient Greeks, over 2,000 years ago, and even the ancient Greeks had calculated that these dates would change slightly over thousands of years into the future, as in the future that is now our present day. So in fact, the sun has now shifted in the actual constellations of the zodiac slightly according to current astronomical observation from those traditional dates that were recorded 2,000 years ago by the ancient Greek astronomer Hipparchus. And the position of the sun in the zodiac on the Prague Astronomical Clock is set according to the traditional dates of Hipparchus. But, nevertheless, the movement of the sun on the dial of the astronomical clock precisely matches those traditional dates. In other words, we can still use the position of the sun on the zodiac dial of the clock to very accurately estimate the date according to the traditional dates for each sign. It just isn't precisely the actual constellation in which the sun is observed to rise each morning. But if the clock survives thousands of years into the future, its zodiac indicator will be exactly correct, once again according to observations, due to the precession of the equinoxes. There are small divisions at the outer edge of the zodiac ring. 6 divisions for each of the signs. 1, 2, 3, 4, 5, 6. Thus each division represents about 5 days. So it is possible, looking very closely, to estimate both the month and day from the position of the sun in the ring of the zodiac. Certainly, it's very easy to identify the season. We can see sort of 4 quarters of this zodiac ring, and this region right here, we're in winter in this image. So this would be the beginning of spring, and this is all spring through here. This is the turn of spring into summer. This region would be summer, and then fall right here. Once you learn the symbols, it's not very difficult to estimate the month, and with close inspection, we could pretty closely estimate the day. In the picture here, it looks like the sun is right at the dividing line between Aquarius and Pisces. So we might estimate the date to be about February 18. Also, it looks like this photo was taken at just before 10 o'clock in the morning. And we can estimate that there's a little more than 7.5 hours remaining of daylight. 1, 2, 3, 4, 5, 6, 7. So we could estimate the sun will set around 5:30 in the evening. Returning to the stereographic projection of the celestial sphere onto the 2D face of the clock, we can identify the very center of the clock with the south pole of the Earth. This fact is contradicted by the image of the globe at the very center of the clock, seemingly identifying it as the location of Prague. This image is only symbolic and a perfectly reasonable choice, representing the fact that this design of the clock's face was built uniquely for the latitude of Prague. Further, we can identify the inner circle here, this circle, as the Tropic of Capricorn, and then another circle for Earth's equator right here. And along the outer rim of the clock, along the edge where we see the Roman numerals here, this is the Tropic of Cancer. Note that the sun will reach the Tropic of Cancer during the summer in the northern hemisphere, and will follow the ring of the Tropic of Capricorn in winter, and will pass through the ring of the equator at the spring and autumnal equinox. Here's an example of the sun's position in June when the sun is at its highest at about noon at the Tropic of Cancer here. Notice the ring of the zodiac is extended by this segmentation. This extension of the zodiac dial has a significance in the geometry of the projection. At the summer solstice, the sun reaches the Tropic of Cancer. Technically, it should be right here. Here's September 22nd at about noon, and we could see that the outer edge here of the zodiac ring is just reaching the equator. So the sun really technically would be right there, just passing over the equator at the fall equinox. Let's switch to December. And here the sun is at its really lowest level at noon in December. And this outer edge of the ring is just touching the Tropic of Capricorn. Finally, the cycle will start again in March. Here the sun is right at the first point of Aries, just entering into Aries from Pisces into Aries and moving from winter into spring. And here once again that outer edge of the zodiac ring just intersecting with the equator. Prague is located at about 50 degrees north latitude, and this location determines the projection of the local horizon at Prague onto the celestial sphere and thus onto the clock's face. The projection of the local horizon onto the clock is shown by the boundary outlined here in red. The clock face is really a map of what is visible when you look up in the sky from Prague. And this circle for the horizon would be the same at any location on Earth at 50 degrees north latitude, and any points that are east or west of Prague at that same latitude would have the same view of the celestial sphere, just shifted in time as the Earth rotates on its axis and the stars and moon and sun appear to rotate across the celestial sphere. The region outside the horizon line is the visible portion of the celestial sphere from Prague, and the clock face illustrates how Prague is far enough north that there is a period around the summer solstice when the sun does not go more than 18 degrees below the horizon, and Prague does not experience the complete darkness of astronomical night. And now there's one more absolutely fascinating timekeeping element to learn about on the astronomical clock, and that's the arm here with a small star pointer at the end. This measures the sidereal time. That means it's counting time based on the stars and not based on the sun. We're used to telling time based on the movement of the sun, but just like this 600-year-old medieval clock, modern astronomers also track time by the movement of the stars, what is called sidereal time in astronomy. The rotation of this little star around the clock's face represents the rotation of the Earth relative to the stars. It represents one rotation of the Earth about the relative fixed background of the stars, and 24 hours of sidereal time is not the same as 24 hours of solar time. This is because the sun is much closer to the Earth than the other stars in the sky, and as the Earth rotates, it also moves relative to the sun. And this means the Earth must rotate slightly more than once around for the sun to return to the same place in the sky each day. Thus, the fundamental unit of measurement, or rotation, a completion of 24 hours, is not the same relative to the sun and to the stars, and counting time by the sun is not the same as counting time by the stars. When the star on the astronomical clock makes one rotation, the stars of the night sky will return to the same place overhead as they were on the previous night. However, measuring this time by a clock that's based on the sun's position, that is by solar time, the stars will return to the same point in the sky a little less than 24 hours later. Also, the star, or sidereal time indicator, this little star pointer, always points in the direction of the vernal equinox, the point that marks the start of spring, Maybe you recognize the vernal equinox as the day that marks the start of spring in the northern hemisphere. But the vernal equinox is also a precise and essentially fixed location in the sky. It's one of 2 points where the apparent path of the sun along the ecliptic intersects the celestial equator, and the other point being the autumnal equinox. On the clock dial, we can see the autumnal equinox directly opposite the point of the vernal equinox, and here in September, as I record this video, this is where the sun's position is on the clock. And then there's the moon, here in this image. The movement of the moon through the sky is accurately captured, as well as its relative position in the sky compared to the sun and the stars, as indicated by its position relative to the vernal equinox. And that relative position accounts for the phases of the moon. There's even a mechanical device built into the movement of the moon in the dial to indicate the moon's phase through each month. It's absolutely fascinating and beautiful, such a remarkable achievement of engineering that captures all of this mathematics, of the projection of the celestial sphere translated into a working mechanism, all built more than 600 years ago, indicating the number of hours until sunset, the time of sunset and sunrise, the day of the year, the month, and the season, and the altitude of the sun in the sky during the year, and the relative positions of the sun, moon, and stars all year long are all accurately modeled year after year. Now it's a math video, so let's end with a quiz. I'll put a few pictures of the astronomical clock at different times and days of the year, and you see if you can figure out what they are.